We are going to look at determining symmetry for functions. We're specifically looking for even symmetry and odd symmetry. We're going to start with even symmetry. An even function is a reflection about the y-axis, and it will have the property f of x equals f of negative x. A good example graph of this is the parabola. Its axis of symmetry, where it is self-symmetric, lines up on the y-axis. For our example work through, we're just going to use a parabola. In this case, we're going to use f of x equals 4x squared plus 2. The first step is to substitute negative x in everywhere that we have an x, and then we want to simplify that. Simplifying, we find that f of negative x equals 4x squared plus 2. We want to note that the parentheses are important when we do the substitution in there. And then we should also notice a pattern as we do enough of these that the even power exponents are going to return a positive x back. We compare the simplified f of negative x to the original, and we see that they match. By the transitive property, we see f of x is equal to f of negative x, and this was our definition property that we were looking for, so we can therefore declare that we have an even function. We are now going to look at an odd function. This is a rotation about the origin. It will have the property that f of negative x is equal to negative f of x. For this example, we're going to use g of x equals x to the fifth plus x to the third. Again, we'll start with substituting negative x in everywhere for x. Simplifying, we want to notice that the odd powers are keeping that negative that we've inserted. We also want to notice that the g of negative x, once simplified, does not match the original, so this is how we know that it's not even. We're now going to go to the second part of this. We're going to multiply everything by a negative, and looking at the definition, we see that the f of negative x is supposed to equal negative f of x. We're going back to the original to multiply everything by a negative 1. As we simplify this, we just find that every sign for every term in the function has just changed sign. Again, we're going to compare this function, the negative g of x, to the g of negative x. We find that those are equal, and so by the transitive property, we have met the definition. Therefore, we can declare that this is an odd function. We can also have neither of these specific symmetries be present in a function. So I'd like to do one last example. I'm going to have h of x equals x squared plus x. Just as we've done before, we're going to start by substituting negative x in for x. We simplify this and we can observe that the x with the even power lost the negative that we inserted. The one with the odd power, namely the first power there, is going to retain that negative. We can go ahead and make that comparison to the original and notice that they do not match, so we can declare that we know this is not an even function. Moving on, we're going to compute negative h of x, and that's just multiplying through by negative 1 again. We can now make this comparison back to the h of negative x that we had calculated and observe again that these are not equivalent either. So we've done both these steps here. We can declare this is not odd, and we know it's not even. Having gone through all these steps, we can now declare that we know that this function has neither of the symmetries that we were looking for. It doesn't have the even symmetry, so it's not a reflection about the y-axis. It doesn't have the odd symmetry. It's not a rotation about the origin. Hopefully this has helped you understand how to determine even and odd symmetry algebraically. Cheerful calculations.